In this video, we're going to be solving this problem. So this is 6-80 in the book Thermodynamics and Engineering Approach by CBK, and this is from the 8th edition. And I'm pretty sure this problem is in other editions, it's just going to be a different number. So this says an inventor claims to have devised a cyclical engine for use in space vehicles that operates with a nuclear fuel generated energy source. So basically we're generating our heat source from nuclear fuel. And it tells us the temperature, and then we have a sink at 490 Rankine, and it says it radiates waste heat to deep space. So basically our sink is just going to be space. And he also claims that this engine produces 4.5 horsepower while rejecting heat at a rate of 15,000 BTU per hour. And we want to know, is this claim valid? Calculate what the efficiency is for this device. And then what we want to do is compare that efficiency to the maximum possible efficiency, which the maximum possible efficiency is going to be for the Carnot heat engine operating between these same two temperatures. So we're going to be calculating two things. We're going to be calculating the thermal efficiency of the device. So let me just write down a few things. We know that this can't be more efficient than a Carnot heat engine, so can't be more efficient than a Carnot heat engine. So we're going to be calculating the thermal efficiency for this cycle, and then we're going to be calculating the thermal efficiency for the Carnot cycle, and we're going to be comparing them. If the efficiency that we calculate for this cycle is higher than the Carnot efficiency for the stated temperatures of the source and sink and for the work that we're producing, then we know that this isn't going to work. So let's go ahead and draw what's going on. So first of all, we have our heat source. So this is T high, and T high is equal to 920 Rankine. And then we have our sink, so this is T low, and T low is at 490 Rankine. So this is just going to be space basically. And then we have our heat engine, and we're not going to worry about drawing all of the components because right now we don't need to know the details of the components. We're just considering the entire engine as our system. So we have some heat that's transferred into the system, we have our heat that's lost, and we have our work. And the work was given as 4.5 horsepower. Alright, so first let's calculate the Carnot efficiency because we know that that's the maximum efficiency that we can have for this heat engine. So the Carnot efficiency, and I'm just going to put this as the maximum efficiency, is 1 over TL minus TH. So this is 1 minus 490 Rankine over 920 Rankine, and this is equal to 0.467. So that means the maximum efficiency that we can have for a heat engine operating between these two temperatures is approximately 47%. Now let's calculate the actual efficiency. So actual efficiency. So this is going to be equal to the net work divided by Q high. And we know the work because it was given. Well, we weren't given Q high. We were actually given Q low, because it says that it's rejecting heat at a rate of 15,000 BTU per hour. So QL is 15,000 BTU per hour. So we have the work and we have Q low, but we need Q high. So we can calculate Q high because we know that the net work is equal to Q high minus Q low. And so then we just solve this for Q high. So Q high is equal to the net work plus Q low. So this is equal to, we want to convert so we have 4.5 horsepower, and we want to convert the horsepower to BTU per hour. So this is, the conversion is there's 2,544.5 BTU per hour, so 2,544.5 BTU per hour per 1 horsepower. And then we know that QL is 15,000 BTU per hour because that was given. So both of our units are in BTU per hour. So that means that Q high is equal to 26,450 BTU per hour. So then we can just plug that into our equation for Q high. We know the net work, and I didn't actually calculate this out. We're going to need this for the net work. This is 11,450 BTU per hour. So then our actual efficiency is equal to 11,450 BTU per hour divided by 26,450 BTU per hour, which is equal to 0.453. So that means that our actual efficiency is approximately 43%. So this is the efficiency that we can theoretically get. That's actually pretty close to our Carnot efficiency. So once we account for losses and other things, this might be really tight, but this could theoretically work.